Hello everyone, my name is Philly. I'm from Civil Engineering Department. So today we're going to present to you about Calculus 3, chapter 16. So here's my content, chapter 16.5, Surface and Area. So we can define curve in the plane in three different ways. Implicit form, y equal to function fx. Explicit form, function fxy equal to 0, parametric vector form. Function or t equal to function ft I hat plus function gt j hat. So we can define analogies in the space. Explicit form z equal to function fxy, and explicit forms function fxyz equal to 0. And also parameterization of surface or function of or uv equal to function f uv I hat plus function g uv j hat plus function h uv k hat. So we can define on the region or in the UV plane is a continuous vector. So the variables u and v's are the parameter, and the parameter domain is R. So here is the UV domain, and function x, y, and z is equal to the function f, g, and h. So let's take a look at an example. Find the parameterization of the cone. So the function that they gave us is z equal to square root of x squared plus y squared, and the domain is 0 to 1. So as you can see here, the cone is related to the polar coordinate. So we need to find the parameterization in terms of R and data. So as you know that x equal to R cos data, and y is equal to R sine of data, and z is equal to square root of x square plus y square. So x square plus y square is equal to R square. So the square root of R square is equal to R. And the domains of radius for R is to 0 to 1, and the theta is 0 to 2 pi. So we can we take the R is u and the theta is v. So we have the function R in terms of R and theta is equal to R cos theta I hat plus of R sin theta j hat and R k hat. So in this surface area, our object is to locate double interval that can be used to parameterize the surface of the curved surface S. So here, this function is we take from the previous one in the previous slide. So we need S to be smooth, and the definition of smoothness is involved to the partial derivative of S that with respect to u and v. So at the below is a partial derivative or u and or v. So the definitions of parameterized surface function or u v equal to function of f uv I hat plus function g uv j hat plus function h uv k hat is smooth curve if all u and all v is a continuous and all u cross product all v is never 0 on the interior of the parameter domain, which means that the all u and all v are not non-zero and never lie along the same line and never and tangent to the surface. So let's take a look the picture below the definition. So as you can see, here's a rectangle area data A sub UV on the UV planes to the elements of data 6 mass of UV on S surface. So we take C1 and C2 tangent to the P0. So the cross product of UVs is normal to the surface of P0. So the element of data sigma sub UV, we assume that that is the parallelogram on the tangent plane. So we have the equation like the magnitude of data U or U cross product with data V or V. Or equal, we can take it the data U and data V out, and it's equal to the magnitude of all U cross product with all V. And by equation 2, we sum this area together to obtain an approximation of the surface area of S. So the sum two ends equal to the magnitude of all U cross product with all V and data U and data V. So the definition, the area of the smooth surface function or UV is equal to function f UV I hat plus function g UV j hat plus function h UV k hat, and with the domain u and v. So the area is equal to the double integral over the regions xy plane magnitude or u cross product with or v dA, or equal to the double integral c to d and a to b magnitude of or u cross product with or v du and dv. So we can write equation for in terms of d sigma. So d sigma is equal to the magnitude of all u cross product with all v du dv, and the integral over the surface d sigma. So let's take a look in example 2. Find the surface area of the cone in example 1. So as you know that in example 1, we just find the parameterization. So here is the parameterization that we found in the example 1. So function or in terms of or and data is equal to or cosine data I hat plus of or sine data j hat plus or k hat. So, and the regions are 0 to 1 and theta 0 to 2 pi. So the first one, we need to find the the partial derivative of or and or theta, and then we need to find the cross product or cross with theta. After that, we find the magnitude of or cross product with or data, and then we find the result is square root of or 2 or. After that, we need to find this the area of the cone. So the area of the cone is the double integral 0 to 2 pi and 0 to 2 1, the magnitude of or u cross product with or v d or d data. So we plug in the square root of 2 or, and then we find the final answer is pi square root of 2 unit square. So now let's take a look at implicit surface. So implicit surface is a function x, y, z equal to c. So let's assume that it is a smooth curve and f is differentiable. Gradient of f is never 0 and it's continuous. And the second is the surface above the region xy plane with gradient f dot with k is never 0. So the formula for the surface area of an implicit surface, the area of the surface function f xyz equal to c over a closed bound and bound the plane region or is surface area double integral over the region's magnitude of the gradient over the gradient magnitude of gradient dot p dA. So right here p is a vector that P is equal to sometimes I, J, or K that normal to the air. So right here, the gradient dot P is never zero if it's zero is undefined. So let's take a look in example 3. Find the area of the surface cut from the bottom of the paraboloid. So the function is x squared plus y squared minus z squared is equal to 0 by the plane z equal to 4. So the function f x y z equal to x squared plus y squared minus z, and the gradient of f is which means that we derivative with respect to x, y, and z. So it's equal to 2xi plus 2yj hat minus k hat. So the magnitude of gradient is equal to the square root of 4x squared plus 4y squared plus 1. And the magnitude of gradient dot p is equal to 1. So, and the dA, the region or dA is equal to dx dy. Therefore, the surface area double integral over the region magnitude gradient f and over magnitude gradient f dot k dA. So right here, as I said in the previous slide that it is a polar coordinate, so we need to convert the function that in terms of x and y into a coordinate. So x squared plus y squared is equal to r squared. So we can substitute x squared plus y squared equal to r squared right here, and the domains we need we found that 0 to 2 pi and 0 to 2. So double integral to 0 to 2 pi and 0 to 2 square root of 4 r squared plus 1 or d data. So the result is equal to pi over 6 times 17 square root 17 and minus 1. So let's take a look the last formula right here. The formula for the surface area of a graph z equal to function f x y. So right here is an explicit form that we use to find the function that in terms of x and y. So for the graph z equal to f function xy over the region or in xy plane. The surface area formula is a equal to double integral over the regions xy plane equal to square root of fx squared plus of fy squared plus 1 dy. Fx right here is equal to the derivative of f in terms of x and derivative, and the y is derivative in terms of y. So you can use both depend on the situation. So if you think that it is easy to find, you can find either of this formula. So thank you for your listening.